The topic is considered to be difficult, but I'll do my best to be understandable and understood. The subject is origin of homochirality, and you understand the word origin, homochirality, I'll try to explain. So let me start that I very much think that at the beginning of every talk, you should have some kind of an abstract. And I was looking for examples of good abstract, and then I found the phenomenal one. The paper is by some British and Indian scientists 12 years ago. The title was, Can Apparent Superluminal Neutrino Speeds be Explained as a Quantum Weak Measurement? And the abstract is very short. Probably not. So my abstract, based on this one, is, do we know what the origin of homochirality is? My abstract, not really. But let's move to the real thing. Before I start talking, I want to tell you what I will talk about. First, after the digressions, I will try to create a tools for this talk. I will define certain terms, and also I'll try to create tools to present three-dimensional chemistry on planar screen. And then I'll talk about homochirality and how we try to address the issue. And then I'll talk about with my friend, Professor Tensor, our contribution to it. Let's start with few digressions. If you came here hoping to learn something which will increase your income, you are in the wrong place. Absolutely not. I guarantee it. I will give you $100 if you show me that I am wrong. Secondly, in history, there were two great Wolfgangs, Wolfgang Amadeus and Wolfgang Pauli, a great physicist. In 1929, he married a cabaret dancer, and a few months later, she left him. And when she left him for a chemist, he remarked in a wonder to a friend, had she taken a bullfighter, I would have understood. But a chemist, can you think of anything else worse than when your spouse runs away with the chemist? Can you think of anything else? I cannot. The point I'm making is we chemists are considered to be dumb, for maybe a good reason. But we have the most intriguing, difficult, important, fascinating, consequential, unsolved problem in science, the origin of homochirality. They may tell you otherwise, but it's our problem, the chemist's problem. So now I think we are ready to move to the real thing. Let's start with definitions. Chirality. The concept was known by great Immanuel Kant in the 18th century. Well, at the time it was Königsberg. They knew that there were two different or opposite Cartesian systems. But the good definition and the name was introduced in 1884 by Lord Kelvin during the Baltimore lectures. I have this question mark here because the book was published in 1904. So the really word spread a little later. Anyway, the point is that an object is chiral if its mirror image is not superimposable on the original object. That's what Lord Kelvin defined chirality. The name comes from chair, hand. Hands are chiral. Left hand, the mirror image of left hand is right hand. And it's not the same. Right hand and left hand are not the same. And these chiral objects, when we talk about very small objects, are called enantiomers. Enantiomers. Enantiomers are a pair of molecules, because the concept applies mainly to molecules, that exist in two forms that are mirror images of one another. Or again, they cannot be superimposed one upon the other. And here's where I took the definition from. I tried to show the simplest one. And I also want to define the word racemate. A racemic mixture racemate is a mixture of both enantiomers, equal amount of both enantiomers, 50-50 mixture of both enantiomers. Let me explain a little better. But before I can explain, let me try to show you the way we present three-dimensional molecules on the plane. This bond and this bond, this is represented by lines, are in the plane of the screen. This thicker line, this thicker bond, is closer to us, closer than the screen. This dotted line connecting this carbon atom with the blue substituents is further from us, further from the screen. This carbon atom has 4 different substituents: a red one, green one, violet one, and blue one. This is the reflection in the mirror: blue against blue, violet against violet, and so on. Moving here, I didn't change anything. It's the same molecule, absolutely the same molecule. Now, let's rotate this molecule around the axis of this bond by 180 degrees. It's the same compound, nothing changed, it just was rotated. And now let's try to superimpose this compound onto this compound, this molecule onto this molecule. Green against green, yes. Red against red. Blue against violet. This compound, enantiomer L, as I call it here, cannot be superimposed on enantiomer D. These are different molecules. These compounds are chiral. Both compounds are chiral. They are enantiomers because the relationship is as the one between mirror object and the mirror and the object. So let's now look at the same situation, but 2 substituents are the same. The violet substituents are the same. Again, those bonds are in the plane. This substituent is closer to us than the screen. This substituent is further from us. Mirror image, the same molecule, rotation again around this axis by 180 degrees is this molecule. Now, green against green, red against red, violet against violet, violet against violet. This molecule is not chiral because its mirror image is superimposable on the original object. Those are not chiral molecules. So this is the picture. And now let's attack the problem. Where is the problem? What is the problem? The problem is that when a chemist performs a reaction forming a chiral compound, the result is always a 50-50 mixture of both possible enantiomers, a racemate. However, a huge majority of chiral compounds found in nature are of single chirality. For example, all sugars belonging to nucleic acid, ribonucleic, deoxyribonucleic, belong to D series, to one type of enzyme, enantiomers. And all enzymes are composed of L amino acids. The amino acids are rarely found, but not involved in enzymes. So let me explain more deeply. I'm a very old man, very old. So I remember things you don't remember. I'm talking about Big Bang. I was very young then, so I remember well. At first, it was only physics. And then slowly, chemistry showed up. Electrons, protons, neutrons, but it was still physics. And then atoms showed up, and then molecules. I remember like today, the first molecules consisted of 2 atoms and the hydrogen atoms. The first molecules were hydrogen molecules. And then molecules became more complex. They consist of more elements, more atoms. Eventually, chiral molecules showed up. And they had to be racemic. They had to produce, the number of both enantiomers produced must have been the same, unless there is a possibility that there was some universal chiral influence acting on the whole universe. We know nothing like this could have taken place. So the first molecules must have been, chiral molecules, must have been formed in the form of racemate, which eventually somehow was separated, or maybe one type of enantiomers was removed from the system. What happened? We don't know, but we'll try to address the problem. Let me explain why racemate must be formed in this case. Again, this hydrogen atom in this methyl group are behind the plane of the screen. Those 2 carbon atoms connected by the double bond are in the plane of the screen. Those 2 hydrogen atoms are closer to us. It's a molecule of propylene. This plane represents is perpendicular to the plane of the screen, and all this hydrogen, carbon, methyl, and hydrogen are in this plane. An oxidation reaction with the oxygen to form the epoxide ring, must take place either from above or below. The chances are exactly the same. Equal amounts of both enantiomers must be formed. Equal amount. Another example. Again, double bond, it's an electrophilic addition of hydrogen bromide. First, proton is added, Markovnikov rule, hydrogen gets connected to the more hydrogenated atom to form the more stable carbocation, and the carbocation is planar. This carbon atom, this hydrogen atom, this carbon atom, and this carbon atom are in one plane. And now bromide anion can attack with equal probability from above or from below. Double bond doesn't have to be part of this. We have an epoxide which we open with hydroxide ion. The attack of the hydroxide ion can be either carbon 1 or carbon 2. This compound is not chiral, but we form the mixture 50-50 of enantiomers. This is the absolute configuration. So if there are no other factors, no chiral influences, the product of the reaction forming chiral compound from non-chiral precursors must be racemic. So let's look at the history of our ideas on what happened, how come. It's intriguing. The first ideas concerning origin of homochirality were described in 1875. It's considered the beginning of the stereochemistry. Lebel in France and Van Hoff. Let me remind you, Van Hoff was the recipient of the first Nobel Prize. So they had many good chemists to choose from, and a great chemist. Lebel and Van Hoff noticed first that if carbon atom or any other atom has 4 different substituents, then there's a possibility for existence of 2 stereoisomers. We call them enantiomers today. And they knew there was a problem. How come in nature there are not enantiomers? At the time, the only chiral influence, the effect which can distinguish between enantiomers, was circularly polarized light, or let's say polarized light. So they proposed to use polarized light in some reactions involving either racemates to deracemize them, or maybe form chiral compounds with, and hopefully with excess of one over the other. The first attempt to perform such reactions took place in 1896, but they were very unsuccessful. The reason was, we know now, the energy of the light was not sufficient to get any success. But some 30 years later or so, there were some successes. The people tried to start with racemate and decompose, and hopefully with different rate, both enantiomers. And they ended up with some small enantiomeric excess, 1%, 3%, 7%, small enantiomeric excess of one enantiomer over the other. The problem is that if you have the small enantiomeric excess in solution, it will soon become racemate again. Racemate is thermodynamically more stable. So it was kind of success, but not really. In 1953, Sir Frederick Frank, great theoretical physicist, wrote a very important paper, which was not that important at the time. A very nonchalant and short paper. He writes essentially that these chemists have a problem with origin of homochirality. Simply, they are not that smart. That's why. But he came up with the idea that the catalyst must not only be a catalyst, but also must inhibit the formation of the opposite enantiomer. It must promote the formation of one enantiomer and inhibit the formation of the other enantiomer. Moreover, the catalyst and the product should be the same. And he introduced the concept of chiral amplification. It was a good story, nobody cared about it. But some 40 years later, Ken Sasoi in Japan came up with the wonderful reaction. I show in a second this reaction. Wonderful, phenomenal reaction. And he explained the reaction greatly. What happens is, it's a very reaction which has nothing to do with origin of homochirality. It's a zinc organic reaction, meaning it cannot be performed in the presence of water, no air, and so on. But as you will see very soon, the reaction very easily produces almost single enantiomer, starting from almost racemate. And sometime later, Christopher Viedma in Spain, a geologist, performed very interesting experiments leading to, during crystallization, to formation of one, even enantiomer, I can say. And recently, the new developments, very important developments, they were started by Naaman in Israel, but some Ostrog at Harvard continued. Let me spend some time here. First, let's talk about polarized light, which I mentioned, that Labelle Van Hoff thought about it. The light, not many chemists don't know it, so I briefly talk about it. The light vibrates in every direction perpendicular to the direction of the light. All the planes, in the plane perpendicular to the light, all the directions are acceptable. And then if this light, here's the circular polarized light, if this light crosses the polarizing filter, it vibrates only in one direction, perpendicular to the direction of the ray. And now, if such a radius are passed through the solution of one enantiomer, this plane is rotated either left or right. Either left or right. And if you have solutions of the same concentration of opposite enantiomers, one enantiomer will cause the rotation, let's say, of 60 degrees to the left. The other, if this concentrations are the same and conditions are the same, the plane of the polarized light will be rotated also 60 degrees, but to opposite direction. So these were at the time the only chiral influences that could be considered. That's why a lot of effort was devoted to polarized light. Let's look at this wonderful SOI reaction. Pyrimidal aldehyde are the substrates, diazopropyl zinc. If you start with very tiny excess of one enantiomer, you can start with a racemate, and let's say quartz is not a chiral compound, but quartz can crystallize in two different forms, which are like enantiomers. And you use small excess of one crystals over the others, and you end up with 99.5 or 99.99, depending on the reaction, in one go of single enantiomer. And note that the product, the starting, and the catalyst have the same structure. Chiral amplification or asymmetric autocatalysis. And as I said, SOI exploits this reaction phenomenally. It's an incredible reaction. However, this specific one cannot be applied to the origin of homochirality. Let's look at the Viedma ripening. Some 40 years ago, a little bit less, Condepodi tried to crystallize this sodium chlorate. Sodium chlorate is not a chiral compound, but can crystallize in two different forms, two opposite forms. And he used stirring, and surprisingly, if crystallization was performed during stirring, he can end up with excess of one type of crystals over the other. Or sometimes even one type of crystals was the only type of crystals. Viedma came up with a better solution. Not only he did this, but he also added glass beads to the system. So crystals were ground during the process, and almost always he ended up in solution with single enantiomer. There was equilibration leading one enantiopode to form the other enantiopode. Only red, only one type of antipodes was formed. Here's the reference I took this picture from, the two Viedma works. But later, Nordruin and Blackmon came up with applying the same technique to compounds where are racemic in every sense of the word, and they could end up with single enantiomer sometimes. and even applied to amino acids. So it has relevance to origin of homochirality. And let me note here that pharmaceutical companies are looking into it. Maybe it's a method to produce enantiomer compounds starting from racemates. Maybe. And recently there's another method which is very important. Some few years ago, Naaman in Israel took advantage of some physics. The point is that if you have magnetic substances like magnetite, Fe3O4, they interact differently with electrons of different enantiomers. And he exploited this wonderfully in these two papers. And then a guy whose name is Osterk at Harvard, he was a postdoc, changed his interest, joined forces with Saselov to apply this to more origin of life related compounds. And eventually they joined John Sutherland. It's a great chemist from now not at Oxford, at Cambridge. Sutherland came up with easy synthesis of riboaminoxazoline, which is RNA, can be used as an RNA precursor. And they used this very compound and some form of magnetite and took advantage of this CISS, it's how the phenomenon is called, and managed to produce very significant excess of one enantiomer of this RAO. I would love to tell you more about it, but there's several reasons I will not do it. The first one is I have no idea what they are doing. So let's move further. It seems to have no influence over the origin of life and origin of homochirality, but it was a wonderful idea which I want to talk about. In 1956, Li and Yang, you may know about it, proposed that when weak interactions are concerned, the laws of physics don't have to be symmetrical. They are not symmetrical, actually. It was very surprising, but a year later, Professor Wu, also a Chinese working in the States, experimentally showed that they were right. She used the cobalt-60 beta degradation to produce some nickel, and the law of the parity was violated. Li Yang got Nobel Prize in 1957. Somehow Professor Wu didn't get it. They wanted very much to, and insisted that she eventually would get it. She never did, but she got a Wolf Award. The consequence was that a few years later, Ulrich Yamagata, eventually great Abdus Salam, thought that translates to the fact that two enantiomers differ slightly in energy. And some papers suggested that not only they differ slightly, L amino acids are of little lower energy and D ribose are of little lower energy. It would be very, very elegant if that was the source of homochirality. Thermodynamically, the enantiomer of low energy would have to become the only one. The problem is that the energy differences are several orders of magnitude too small to have any effect of the origin of homochirality. But it's a very interesting concept, therefore I wanted to mention it. And there are several answers which were at a certain point considered to be very attractive and may become attractive again. First, Eschenmoser and also Gadiri noticed, and some others, that rate of homochiral and heterochiral polymerization may not be the same. So maybe we may start with racemate, but produce polymer with excess of one enantiomer, or maybe even homochiral polymer. But so far, we don't have good experimental results. Also, some 15, 20 years ago, it was noticed that if you start with substantial excess of one enantiomer, and distill the mixture, you can enrich the mixture. It applies to sublimation, crystallization. At the moment, I don't believe there's any importance of them to Origin of Homochirality, but things may change. Now, I have some time. I would like to tell you a little bit about what, with my friend Michael Tenser in Ottawa, what we propose. And I'm not saying we are main stream, but we are recognized to some extent. First, we noticed that 3 orienting factors, which, if they are perpendicular to each other, is a chiral influence. And when I say orienting factors, a molecule which consists of hydrophilic and hydrophobic end at the interface water-oil is oriented, or molecules are with non-zero dipole moment are oriented in the electric field. So let's look at these molecules. These 2 are enantiomers, and they are just above the surface. This plane represents the surface. G represents the vector of interactions of these molecules with the surface. D2, let's not enter at the moment what D2 is, but D2 is such that X, which is further from us, and Y is closer from us. So that's the orientation of this molecule. X is always, in both cases, further from us. And D1 is another orienting factor, which causes that this carbon atom with substituents R and Z is on the right, but this double bond with Y and X substituent is on the left. It's the same in both enantiomers. Then you see that one enantiomer has Z interacting with the surface, the other enantiomer has R interacting in the surface. The energy of interaction with the surface is not the same. Let's imagine that we now introduce a movement of a solvent, like in chromatography. Then these compounds will dissolve and be adsorbed again, dissolved, adsorbed many times, but the energy of interactions will be different, and they will move with different rate through the column or through the plane. Let's note something else. Here, this carbon atom is not chiral. These carbon atoms are chiral. 1A and 1A prime is a pair of enantiomers. 2A and 2A prime are also a pair of enantiomers. These compounds say 1A and 2A are just stereoisomers, diastereoisomers to be more precise. Note that here both hydroxyl groups are below the plane, meaning closer to the surface. Interactions with the surface, if they are via hydrogen bonds, are the strongest. Here, there are no hydroxyl groups down interacting with the surface. So this molecule will move the fastest. For these 2 molecules, there's only one OH group directed towards the surface, so they too should move somewhere in the middle. The point I'm trying to make, and again, the G, F, and E factor orient molecules. The point I'm trying to make is that this method, we call it absolute enantiomer selective separation, not only can separate enantiomers, but also stereoisomers, diastereoisomers. That is important, and I'll try to show you why. So first, amino acids. This rectangle, I couldn't get rid of it. It's here. When I moved from normal file to this, to the PowerPoint file, it would show up. Anyway, I want to point out, this is amino acid. This carbon is chiral, it's a chiral center, and at most there's one chiral center in the R group. Amino acids have at the most 2 chiral centers. Sugar have more. And in particular, the most interesting of sugars is ribose. Why? Because if the molecules are oriented in such a way that this oxygen in the ring is further from us, as shown here in both enantiomers, and this carbon atom bonded to 2 oxygen atoms, this hemiacetylic carbon atom, is on the right, then in one of the riboses, all hydroxyl groups are down, let's say towards the surface. In the opposite enantiomer, all hydroxyl groups are up. meaning the difference interactions between two enantiomers, in this case, are the biggest, the strongest. So the first sugar may have more chiral centers than amino acids, and alpha DL, racemate of ribopyranols, is unique because as many as 4 hydroxy groups are either towards the surface or against the surface. So let's move on. The question is, what was the first surface, absolute natural surface? Recently, we sent it to astrobiology more than 3 months ago, and we know some friend of us told us that he had to refuse being a reviewer because it was sound. Anyway, the point is, if you introduce nucleobases, all of them, but particularly interesting is guanine and cytosine. Nucleobases are those compounds connected to ribose in nucleic acids, connected to carbon atom 1 of ribose. If they are located on a flat surface, the surface becomes chiral, and you can have different interactions with different enantiomers. So we proposed that some 4 billion years ago, the ribose was separated from L-ribose on chiral domains. The green lines represent interactions between the cytosine guanine. This is guanine, this is cytosine. This is Watson-Crick hydrogen bonds. Very strong interactions, but you can have 8 green lines per system interacting with the surface. So, and experimentally it's been shown, it's relatively easy to form homochiral domains of similar nucleobases on the surface. And if you build a model, you can see that there's a difference of interactions between left and right, between L and D ribose. But it's very difficult to show it on the plane, so I didn't even try to do it. The question, which has nothing to do with origin of homochirality, is the question, why ribose? Nucleosides contain ribose, the furanose form, but great Albert Eschenmoser, he died a few weeks ago. I want to digress here. One of the greatest chemists of the 20th century. I have no idea why he didn't get the Nobel Prize. He did phenomenal things in the chemical synthesis, but from my perspective, more importantly, he entered incredible research. He thought, why did nature choose ribose? Let's try some other sugars. And they could synthesize a variety of equivalent of nucleic acid containing ribose, but other sugars, ribose in the pyranose form. And it turns out that many of these products were better from any point of view of properties than nucleic acid. So why did nature choose ribose? Why? The answer Albert Eschenmoser proposed is, in principle, it was not because ribose was the best, but nature didn't have anything else, was sentenced to use ribose. So what we are saying, with my friend, is that ribose was the only sugar nature could have separated to enantiomers. Ribose, D-ribose, became available, and formation of nucleotides, and further life, the necessary condition for this was the presence of enantio-pure ribose. That's our hypothesis. We are not saying we have any evidence. That's what we think. So we believe that our story is as follows. First, there was Formose reaction. I still have a few minutes. Formose reaction, which is reaction of formaldehyde with some base, calcium hydroxide. Butlerov in 1859 discovered this reaction. Eschenmoser and some others created simpler versions, producing much less complicated mixture. The mixture consists of monosaccharides, tetroses, pentoses, hexoses, troses, all of them, of course, in the racemic form, but sugars. So Miller-Urey experiment in 1953, forming a mixture of amino acids, was kind of much later than the Butlerov's experiment. Anyway, first, many sugars were formed as the result of Formose reaction. Then absolute and enantiomer selective separation took place on the chiral surface. Likely solvents, formamide, hydrogen cyanide is a wonderful solvent, water, carbon dioxide, formic acid. Possible structures, homochiral domains. If one homochiral system shows up, then it can force the next ones to be of the same chirality. So homochiral domains or nucleobases, we believe it was guanine cytosine. This one seems, by our calculations, also to be the best. Since D-ribose moved slower than other monosaccharide, it became isolated from the mixture. Nature isolated enantiomer, 100% pure D-ribose. Next, nucleosides and nucleotide was formed. Nucleosides with addition of the base, nucleotide phosphoric acid. The RNA world followed. What is the RNA world? Some 40-something years ago, it was noticed that nucleic acid, RNA, can act as catalyst, as proteins. So somebody came up with the idea that the system is too complicated to be formed in one go. The first life was based on RNA only. There were no proteins involved. And it's a very likely hypothesis, which is considered to, not by all, but by many, the very reasonable hypothesis. So our scenario is perhaps not very exciting when we talk about the origin of homochirality, but we answer some other questions. First, why amino acids were preceded by sugars? Question which was raised many times in the last 30, 40 years. Our answer is that the number of chiral centers in amino acids is insufficient. It has to be as many as 4, like in ribose. How the first racemate was separated under abiotic conditions? Absolute and antiseptic separation. Why ribose? Because there are as many as 4 chiral centers with hydroxyl group either towards or against the surface. And here perhaps the most important argument we offer is that most methods don't talk about separation of the selected compound from other garbage. We do say AES is a chromatography-like process. So separation of D-ribose meant separation from L-ribose, but also from other enantiomers, diastereomers, and whatever the mixture components were there. So conclusions. Origin of homochirality is nagging but intellectually stimulating unsolved problem of science. Let me emphasize, from my perspective, is by far the most important, by far the most nagging. Physicists may tell you whatever they want. Chirality is the problem which biologists, chemists, and physicists are very much interested in. Homochirality, its origin, it's our problem and very important problem. Moreover, the solutions may offer a variety of answers valuable for today's chemical industry. For decades, there were no answers whatsoever. Then at a certain point, we thought we had too many answers. But now we have a few acceptable answers. However, let's make one point. Every few years, you look in Wikipedia, there's some new stuff. Somebody came up with some ideas, and his students, or he or she himself, put the text in Wikipedia that essentially the problem has been solved. I solved it. Life is great. No. We still are far away from satisfactory answers. Perhaps some looking into preparatory fossils will offer us the evidence to support one of the existing hypotheses. And finally, perhaps it's not a conclusion, but I deeply believe, and not everybody will agree with me, that availability of enantiomer compounds is a necessary condition for life to begin. So those are my conclusions. This is the end, and thank you for your forbearance. That's all I've got.
Wow, that's very good. Thank you very much for doing this. We really appreciate it.
Did I bore you to death? I tried.
No. It's just fascinating. It's it's almost like a philosophical question.
Questions? Are there any? I'll try to answer if I can.
Yeah, I have a question I didn't catch. Why the D ribose move so slower than the others?
Because if you have in the nucleic acid ribose in the furanous form, but in solution there's a mixture of all the forms. So on the surface you will have mainly or only pyranose form, six-member ring system with oxygen in the ring. And now, if the interactions of other atoms in the ribose, this oxygen in the ring, for example, with the surface is such that both ribose units are oriented in the same direction, in two directions, then in one enantiomer, all four hydroxyl groups are directed towards the surface. If the surface is, let's say, polar or hydrophilic, it will interact very strongly to slow down the movement. The other enantiomer have all hydroxyl groups directed against the surface, further from the surface. So there are no these strong interactions. So this enantiomer will move much faster with the movement of solvent.
All right, I see.
Well, the problem is we are talking of processes on the surface. The others also. So you cannot end up with significant amount of compound. You can use some physical methods to show your point. But nature had a lot of time to produce. She can produce a lot of compounds, even working on the surface. It's difficult in the lab to produce enough compound to prove your point.
I have a question, Roman, about AES, absolute enantiomeric separation. How practical is that? Has it actually been reduced to practice, or is it a theoretical concept?
No, it's not. I can argue it can become practical. We published some papers on it, but the point is we are working on the surface. The size of the reaction in bulk and on the surface, the difference is 10 to the power of 7. So you have to work with exceptionally small amounts, even on huge surfaces. However, I may be wrong. Again, nature could have used, kilometers of surface. I can use small surfaces. So no, at the moment it's not practical at all.
There was a related theory a number of years ago, I think, that the resolution, the separation of the enantiomers of some biological material, sugars or amino acids, was achieved on chiral inorganic substrates, essentially crystals of minerals.
Yes, well, there were several papers. Interesting. Hazen published in 2001. In 1980, Thorby published papers. Yes, if you have chiral crystals of calcite, of quartz, you can, but you end up with exceptionally small amount. And it's not that they really separated. Using physical methods, they showed that there's more adsorbed of one enantiomer than the other. But these are very, it's the same thing as this using of circular polarized light. You end up with a slight excess, and what's then?
Okay, thank you.
Let me ask a quick question. Maybe it's what if you were to feed let's say a bacteria instead of having the nucleic giving a protein, okay, that is synthesized, and it's not an L protein, but it's a D protein. What is the can nature, can a bacteria use the wrong type of amino acids? Or better yet, if you have sugars, and you would be using the wrong kind of sugars, how is the nature going to be dealing with that?
The nature won't be happy with you. No, nothing will happen. However, amino acids belonging to proteins are 100% L amino acids. However,
Right.
nature uses D amino acids in cell walls. So perhaps, and I don't know, perhaps say bacteria can use D amino acids to build cells, maybe, but I don't believe they can racemize or can change the chirality from L to D or vice versa. I don't think
Okay.
so.
Thank you.
They can distinguish, enzymes do distinguish, enzymes produce only one enantiomer, but they are chiral, therefore they can do it. But I don't believe they would be happy with opposite enantiomers of this living, of the compounds belonging to living organisms.
I have one other simple question. You remarked about halfway through that racemates are more thermodynamically stable. Is that correct? And if so, why would that be? The racemates being more stable than either enantiomer.
I'm not sure why, but experiments show that if you have the mixture of small excess of one enantiomer, leave it for some time under almost any conditions, it'll racemize.
Huh. Interesting.
I cannot tell you why, but it's kind of, I don't know.
Well, very good. I really appreciate you giving us this fascinating talk. And are there any other questions? No. All right. I think that we are able to conclude this meeting. Does anybody have any other notes or suggestions or comments? Okay.
Thank you and goodbye.